Welcome to your Learning Den. Today, you're joining us for a really fascinating exploration. It was actually sparked by an amazing video from Veritasium.
Oh, yeah, the one on Emmy Noether. Fantastic stuff.
Exactly. So huge thanks to Derek Muller for, putting that out there and inspiring this deep dive.
Definitely. And what we're going to unpack is, well, it's pretty remarkable. We're talking about Emmy Noether.
Right, a mathematician maybe not everyone's heard of, but wow.
Absolutely. Her work didn't just tweak things. She fundamentally changed how we get why certain laws of physics, these really basic laws, even hold true.
And it's this incredible story of how she challenged and actually corrected a really key part of Einstein's early work on general relativity.
That's the core of it. How she showed his first take on energy conservation in GR had a serious problem.
And in doing that, this is the amazing part, she basically handed physics this profound insight, this link between symmetry and the laws governing everything.
It's genuinely mind-blowing. And look, if physics isn't your main thing, don't worry.
Yeah, we'll break it down step by step. Focus on the main ideas, the impact.
You'll get it.
Yeah.
Prepare for some definite aha moments, I think.
Okay, let's kick off with that thought experiment from the video. It really sets the scene.
The astronaut and the rock.
Yeah, you're out in deep space, total emptiness, and you throw a rock.
Hard. Okay, I'm picturing it.
Now, Newton's first law, basic physics, right? It suggests that rocks should just keep going. Straight line, constant speed, forever.
Right. Object in motion stays in motion unless something acts on it. That's the classical idea.
But, and here's the twist the video highlighted, in reality, that rock would actually slow down.
Yeah.
Eventually, it would just stop.
Whoa, hang on. That feels like it completely breaks Newton's law.
It does seem like it. So the puzzle is, why? Where does the energy go? It has to go somewhere, right?
Well, this little puzzle actually points to a much, much deeper issue, something physicists, including Einstein, were really wrestling with around the time he was developing general relativity.
Okay, so speaking of Einstein, the sources mentioned 1915. He's at the University of Göttingen.
That's right. Giving these 6 lectures on his brand new theory of general relativity, still kind of a work in progress, actually.
The theory that gravity isn't a force, but space-time bending.
Exactly. Curvature caused by mass and energy. But yeah, the math wasn't totally nailed down yet.
And one big hurdle he had was energy conservation. How does that fit into this new picture?
A huge hurdle. Because, energy conservation energy isn't created or destroyed, just changes form. That was like bedrock physics. How do you show that holds up in this new curved space-time reality?
Okay, so Einstein's stuck on this energy thing. And then another big name enters the picture, David Hilbert.
Ah, yes. Hilbert, a mathematical heavyweight. He was actually in the audience for Einstein's lectures.
Really? And he got hooked on this energy problem, too.
Totally fascinated. He started digging into Einstein's equations himself, trying to find mathematical proof for energy conservation within the theory.
And what did he find? Did he solve it?
Well, sort of, but not really. He found these things called the Bianchi identities, mathematical relationships.
Bianchi identities. Sounds important.
They are important mathematically, but here's the catch. They showed something was conserved, yes, but only if the universe was completely empty.
Empty, like no stars, no planets, no anything.
Exactly. Zero matter, zero energy, which, isn't exactly our universe.
Right, kind of useless for describing reality then.
Pretty much. So even Hilbert, brilliant as he was, hit a wall on the energy conservation front. It seemed like these identities didn't help.
Okay, so Einstein's grappling, Hilbert's hit a dead end. Sounds like they needed someone new, someone with a different angle.
Enter Emmy Noether. Hilbert actually brought her in as his assistant. He saw her talent.
And she was perfectly placed to tackle this. But her own story getting there,
Yeah.
it wasn't easy, was it?
Not at all. It's crucial context. Her dad was a math professor, so she grew up with it, loved it.
But being a woman in academia back then,
Yeah.
huge obstacles.
Massive. Just to even attend lectures at university initially, they basically said no because she was a woman, said it would cause chaos.
That's just unbelievable. But she kept going.
She did. She eventually got to spend time at Göttingen learning from the best. And crucially, she got really deep into the mathematics of symmetry.
Ah, symmetry. That seems to be the key word here.
It's everything. That time at Göttingen, learning about symmetry, that set the stage for her huge breakthrough.
Okay, let's unpack symmetry. The video used that equilateral triangle, right? How does that illustrate it?
Perfect, simple example. Equilateral triangle, all sides equal, all angles equal.
Right.
Now, if you rotate it by 120 degrees, it looks exactly the same, doesn't it?
Yeah, it lands right back on itself.
Do it again another 120 degrees, same thing.
Right.
Or flip it over certain lines, reflections, it still looks identical.
So those actions, the rotations and flips, those are the symmetries, transformations that leave it unchanged.
Exactly. But then you take that idea beyond just shapes.
Right. The video mentions symmetry in math functions too. How does that work? It feels more abstract.
It is more abstract, but super powerful. Imagine plotting a function like a sine wave on a graph.
Okay, got it. The wavy line.
Now, if you slide that whole graph sideways along the x-axis, the specific points move, obviously, but the shape, it's still a sine wave, right?
Yeah.
Oh.
It looks the same, just shifted over.
That's a symmetry, too. The underlying mathematical relationship is unchanged by that shift. And unlike the triangle-specific rotations, this can be continuous. You can shift it by any amount.
Okay, continuous symmetry. Got it. And Noether became a master of this stuff.
A world expert.
Yeah.
She eventually got her PhD in math, only the second woman in Germany to do so, fighting those barriers all the way. And she brought this deep knowledge of symmetry to that energy problem Einstein and Hilbert were stuck on.
So Einstein had actually proposed some kind of solution, right? An equation.
He had, yeah. He was trying to make it work. His idea was basically, okay, take all the energy from matter and radiation.
Like stars and light.
Right. And add to that the energy stored in the gravitational field itself. He proposed that this total sum would be constant, conserved.
Seems logical on the surface. You count for everything, including gravity's energy.
It does seem logical, but Noether apparently looked at it and immediately thought, no, that's fundamentally wrong.
Why? What was the flaw she saw?
Well, her gut feeling, backed by her mathematical insight, was that Einstein's proposed equation clashed with the absolute bedrock principle of his own theory. General covariance.
General covariance. Okay, refresh my memory on that one. Why is it so central?
So back in 1905, Einstein had special relativity, right? Laws of physics look the same for observers moving at constant speeds, inertial frames. But he wanted to go further. What about accelerating observers, or observers in gravity? He wanted the laws to look the same for everyone, no matter how they're moving. That's the general part.
So the laws of physics shouldn't depend on your point of view, basically.
Exactly. They must have the same mathematical form in all coordinate systems, all frames of reference. That's general covariance. It's the foundation.
And didn't his happiest thought connect to this? The falling window cleaner.
Yes. The famous thought experiment. If you're falling freely, you don't feel your own weight, right? You're weightless.
Like an astronaut floating.
Precisely. It's indistinguishable locally from being in space far from gravity. This led him to the equivalence principle. Gravity's effects are locally equivalent to acceleration.
Which meant gravity wasn't a force in the old sense.
Right. It was a manifestation of space-time curvature. And to make this theory work for all observers, to make it generally covariant, he needed a special mathematical language.
Tensors, that's where they come in.
That's where they come in. Tensors are mathematical objects that describe physical quantities in a way that's independent of the coordinate system you choose.
So they capture the real thing, regardless of how you measure it.
You got it. They stay the same, mathematically speaking, even when you change frames of reference. That's why they were essential for building a generally covariant theory like GR. The laws written using tensors would automatically be the same for everyone.
Okay, so GR demands general covariance, which demands tensors. Now back to another looking at Einstein's energy equation. What was wrong? You mentioned a pseudotensor?
Exactly. That was the smoking gun for Noether. Einstein's equation, the one trying to add up matter energy and gravitational energy, contained this thing called a pseudotensor to represent the gravitational energy part.
Pseudo. So like fake tensor.
Pretty much. It looks like a tensor, but it doesn't behave like one when you change reference frames.
Meaning?
Meaning the value you calculate for gravitational energy using this pseudotensor depends on the observer. You could literally make gravitational energy appear or disappear just by changing your coordinates, your perspective.
Wait, so the amount of energy isn't objective. It depends on how you look. That can't be right for a fundamental law.
Precisely. Noether's point. If energy conservation depends on the observer, it's not a real fundamental conservation law baked into the theory's structure. It's an artifact of the description.
So Einstein was kind of forcing the old idea of energy conservation onto his new theory, using a mathematical trick that didn't quite fit.
That's a really good way to think about it. He wanted energy conserved, but the tool he used, the pseudotensor, violated the theory's own core principle of general covariance.
And Noether saw this conflict.
She saw the deep tension, and it led her to ask this absolutely pivotal question. What if general covariance and energy conservation, at least in the traditional sense, are actually incompatible?
Incompatible. Like, you can't have both within general relativity.
What if the very structure of GR, its general covariance, prevents energy from being conserved globally in the way people thought? And if so, why? That's the question she set out to answer.
And this is where her own theorems come in, her famous theorems.
Exactly. She tackled it by looking at the symmetries of the universe, starting simple. Imagine that empty, static universe again.
Okay, nothing in it, not expanding.
Right. In such a universe, one point in space is just like any other, right? There's no special center.
Makes sense. Complete uniformity.
That's a symmetry. Translational symmetry in space. The laws of physics are the same everywhere. Noether showed mathematically that this directly leads to the conservation of momentum.
Wait, just like that, space being the same everywhere means momentum must be conserved.
Precisely. If you throw that ball and the laws are the same over here as they are over there, there's nothing to change its momentum. It just keeps going. One follows necessarily from the other.
Wow, okay. What about other symmetries in this simple universe?
Well, it also looks the same no matter which direction you're facing, right? Rotational symmetry.
Uh-huh.
Noether proved that rotational symmetry directly leads to the conservation of angular momentum. Why does a spinning top keep spinning? Because space is rotationally symmetric.
Mind blown. Okay, so spatial symmetry gives momentum conservation. Rotational symmetry gives angular momentum conservation. What about time?
Good question. What about the symmetry that the laws of physics don't change from moment to moment? Time translation symmetry.
The idea that an experiment done today gives the same result tomorrow.
Exactly. Noether dug into this using some advanced concepts like the Lagrangian, basically kinetic minus potential energy, and the principle of least action.
Okay, don't need all the math details, but the upshot.
The upshot is profound. Noether proved mathematically that this time translation symmetry, the laws being the same over time, is the reason energy is conserved.
So conservation of energy isn't just some rule. It's a consequence of time symmetry.
It is a consequence of time symmetry.
Yeah.
Her first theorem revealed this incredible pattern. Conservation laws aren't fundamental on their own. They emerge from the symmetries of the underlying physical laws or space-time.
That completely changes how you think about physics. Symmetries are the truly fundamental things.
It was revolutionary. For centuries, conservation laws were just observed facts. Noether explained why they exist.
Our actual universe isn't empty and static.
Yeah.
It's expanding. How does that affect things?
Now we get to the really interesting part. The discovery that galaxies are moving away from us, and the expansion is accelerating. That tells us something crucial.
What's that?
Our universe is not symmetric in time on the largest scales. The universe billions of years ago was very different from today, and it will be different in the future. It's evolving.
So no global time symmetry.
Not on cosmological scales, no. The symmetry is broken by the expansion itself.
And if time symmetry is broken, does that mean?
It means exactly what you think. If the symmetry that guarantees energy conservation is broken globally, then energy conservation itself isn't globally guaranteed.
So energy isn't conserved in the expanding universe. Seriously.
On the scale of the entire cosmos? No, not in the strict traditional sense. Think about that light from the early universe, the cosmic microwave background.
Yeah.
As the universe expands, the wavelength of that light gets stretched out. Longer wavelength means lower energy. Where did the energy go? It was lost due to the expansion of space itself.
And the rock the astronaut threw, why does it stop?
Same basic reason. The expanding space does work on the rock, stretching things out, diluting its momentum and energy over vast distances and times. The energy isn't conserved globally because the underlying time symmetry isn't there globally.
Okay, that is genuinely hard to wrap your head around. Energy not being conserved feels wrong.
It feels wrong based on our everyday experience.
Right, because locally, like here on Earth, in our labs, energy conservation seems to work perfectly. Why the difference?
Because locally, and over the short timescales we usually deal with, the universe's expansion is incredibly, incredibly tiny. So time translation symmetry is an excellent approximation.
So it looks symmetric to us locally.
Pretty much perfectly symmetric. So energy appears to be conserved to extremely high precision in our labs and daily lives. It's only when you zoom out to cosmic scales in billions of years that the lack of perfect symmetry, and thus the lack of perfect energy conservation, becomes apparent.
Okay, that makes more sense. So Noether's first theorem explained global conservation laws and why energy isn't globally conserved in our universe. But what about the original problem, energy in GR itself?
Right, the problem Einstein and Hilbert couldn't solve. That's where Noether's second theorem comes in.
Another one.
This
Sure.
one deals with local symmetries. See, even though global symmetries like time translation are broken in curved, expanding spacetime, general relativity still has that fundamental local symmetry, general covariance.
Walls looking the same locally no matter how you move.
Exactly. The physics in your little patch of spacetime follows rules that look the same regardless of your coordinate system or motion, thanks to tensors.
So what does this local symmetry give you, if not a global conservation law?
It gives you something called a continuity equation. Think of water flowing through pipes.
Okay, pipes and water.
A continuity equation just says that the change in the amount of water in one section of pipe has to be balanced by the flow of water in and out of that section. Water doesn't just appear or disappear within the section, it flows.
Makes sense. Conservation of water within that local bit of pipe.
Exactly. Another showed that in GR, because of the local symmetry of general covariance, you get a continuity equation for energy and momentum. In any tiny patch of spacetime, energy flow is balanced locally. It looks conserved right there.
But only locally.
Only locally. When you try to add up these local patches over a larger region of curved spacetime, the curvature itself acts like, well, like connections or maybe even leaks between the patches.
Leaks, so energy can leak out, in a sense.
In a way, yeah. Energy can be exchanged with the gravitational field itself due to the curvature in a way that messes up a simple global addition. The local continuity holds, but it doesn't sum up to a global conservation law because of the spacetime curvature.
And this continuity equation she derived,
Yeah.
how did it relate back to Hilbert?
Here's the kicker. The mathematical form of Noether's continuity equation derived from local symmetry. It turned out to be identical to those Bianchi identities Hilbert had found earlier.
The ones he thought were useless because they only worked for an empty universe.
Yeah. The very same. Narita showed they weren't useless at all. They were the correct statement about energy momentum flow in GR. They represent the local conservation, the continuity equation, which is the most you can say about energy conservation within the full theory of general relativity.
Wow. So she basically reinterpreted Hilbert's result and showed it was the actual answer, just not the answer they were expecting.
Precisely. She showed why you don't get global energy conservation and what you get instead, this local continuity dictated by the Bianchi identities.
So with these two theorems, it's just staggering. She explained the origin of all conservation laws via symmetry, and she solved the energy puzzle in GR that stumped Einstein and Hilbert.
Monumental achievements. Just absolutely fundamental contributions to physics.
Did Einstein recognize how important this was?
Oh, absolutely. He deeply admired her. In the obituary he wrote for her in the New York Times, he called her the most significant creative mathematical genius thus far produced since the higher education of women began.
That's incredible praise, especially from Einstein.
It really shows the level of respect she commanded despite the barriers she faced.
And her work wasn't just about fixing GR, right?
Hmm.
It changed how physicists thought about everything.
Completely. It shifted the whole mindset. Physicists started thinking, what are the symmetries? Because the symmetries will tell us the fundamental laws and conserved quantities.
Like a new toolkit for understanding the universe.
Exactly. And it's been unbelievably successful. Her ideas are crucial in quantum mechanics, particle physics. Understanding why electric charge is conserved comes from a type of symmetry called gauge symmetry.
So it connects to fundamental particles' forces.
Quarks, the Higgs boson, the nature of forces like electromagnetism. Noether's link between symmetry and conservation laws is woven through all of modern physics. It's foundational for any attempt at a theory of everything.
It's just such an inspiring story, especially given the context. You mentioned the Nazis. That affected her career terribly later on.
Tragically, yes. Even after all her achievements, getting a proper paid position at Göttingen took years. Then, in 1933, because she was Jewish, the Nazis dismissed her. Awful.
But there's this incredible story that even after being banned, she kept teaching math in her home. Just pure dedication. Eventually, thankfully, she was able to emigrate to the U.S., taught at Bryn Mawr College.
Until she passed away relatively young, right?
Yes, sadly in 1935. But her legacy was already immense and continues to grow.
So wrapping this up, this deep dive really shows how Emmy Noether, using this deep understanding of symmetry, didn't just find a flaw in Einstein's early ideas about energy and GR.
Though she did do that.
Right. But much more fundamentally, she revealed this incredible principle connecting symmetry to the conservation laws that rule the universe.
Yeah, pause on that for a second. Those rules we take for granted, energy momentum, angular momentum, they aren't just random. They come from the symmetries of reality.
And where the symmetry isn't perfect, like time symmetry in our expanding universe.
Then conservation law isn't perfect either, at least not globally. Energy isn't strictly conserved on a cosmic scale. Another gave us the why. It's just a more profound, more elegant way to understand physics. Not just correcting a mistake, but providing a whole new framework.
It really highlights the power of pure mathematics to unlock secrets about the physical world. It's beautiful, really.
Absolutely. And we've really just, scratched the surface here. There's so much more to know Noether's work and its impact.
Definitely encourage people to read more about her.
Mhm.
Her life, her theorems, they're foundational.
It makes you wonder, doesn't it? What other symmetries are out there? What other laws might emerge from them?
And what does non-conserved energy in cosmology really imply for the ultimate fate of the universe? Big questions.
Definitely something to mull over. A true deep dive into the fabric of reality, sparked by one brilliant mathematician.